we're going to look at that radial heat transfer. It's similar to what we did previously, except we're going to do this now using shape factors. And now, if you've forgotten how to do this, you can probably review the video linked below. Or as I go through this, a lot of this might come back, and you might not even need to go back and study that previous video. So again, if we're looking at heat transfer, and we're going to look at again through radial shapes, in other words, through a pipe in particular. And remember, we did previously for we calculated Q equals delta T divided by the resistance of our system. And remember, we kind of added up all the resistances, and for each resistance, let's say for convection, if it's radial, that was going to be 1 over HA, and that was going to be 1 over H, and the area was going to be the circumference, which is pi d, times the length. So, if you maybe had something, we had like maybe a pipe like this, it's going to be the length of the pipe, and then times pi times the diameter. Again, this is going to be the circumference, so the circumference times the length is going to give us like the radial area. And then for conduction, we had log, and let's say you had 2 diameters, it would be like, say, D2 divided by D1, all divided by 2 pi K times L. Again, this is going to be for radial conduction. This is going to be the resistance for radial conduction. And remember, H is the heat transfer coefficient and K is the thermal conductivity. And so we're going to be using that. And then also, we're going to need to calculate what's called our shape factor. And we'll look at that in a minute. So we're going to need, so for certain objects, we're going to have, and let me just call that RS for times we have to use shape factor. It's going to be the thermal conductivity times S, where S is found in our table. So we're going to go through a problem where we use all this stuff and we put this into our heat transfer equation. Again, remember, this R is going to be all the resistances added up, and we'll see that in our next example. So let's take a look at this example. Water is flowing through a steel pipe buried in the ground. The water is at 190 degrees Fahrenheit. The center of the pipe is 4 feet below the ground surface. And the ground surface is at 20 degrees Fahrenheit. The inside diameter of the pipe is 3 inches. The steel pipe is 0.375 inches thick. The pipe is covered with 1.25 inches of thick of insulation. The water has a convective heat transfer coefficient of 2275. The steel pipe has a thermal conductivity of 50. The insulation has thermal conductivity of 0.013. The soil has a thermal conductivity of 0.12. A lot of information there. But here's the picture. You can see there's soil, and you have the water, which is the fluid flowing through the pipe. And the pipe is uh, 4 feet below the ground surface. And here you see it's called Z because that's what we're going to find in the table. It's going to be characterized by Z. And we can even maybe take a look at, say, the inside of the pipe. We have something like this. We have our fluid, which is water. Then we have the steel pipe. Then we have insulation. And we can call this inner diameter D1, the other one D2, the other one D3. So let's take a look at this. So we have our fluid flowing through the steel pipe, and the fluid, of course, is water. And there's soil here, the ground, and the surface temperature at the top of the ground is 20 degrees Fahrenheit. The solid pipe is 4 feet below the ground surface, and so this is going to be 4 feet, like this. And uh, we have our information given, and you can think that we have something like this. And actually, I'm going to put some of these diameters on in feet. So the diameter of the pipe is 3 inches. So it's going to be 3/12, of course. That's going to be 0.25. And then that's D1. And then D2, the thickness of the pipe is 0.375. So for D2, we're going to have 3 inches plus 2 times 0.375 and divide that by 12. And then we're going to have a D3 was it's going to be this outside diameter of the insulation is a 1 1/4 inch thickness of insulation. So we're going to be adding to this. We're going to add two more of those. So D3 is going to be 0.3125 feet plus we have the thickness 1.25 times 2, divide that by 12. So then D3, like this. So there's D1's 0.25, 0.3125, 0.52, 833. Now we're going to solve this problem using shape factors. And it's very similar to how we dealt with radial convection conduction before. In fact, if you've forgotten, look at the link below to show how the basic way of handling this. And it's going to be very similar to what we're doing now, except we're going to include shape factors, which gives us a better estimate of the values for the heat transfer. So let's go ahead and do this. So I'm going to kind of do this in steps. I'll put together, say, for water. So the water is flowing through that center, the center of the pipe there. We know the diameter is 0.25. Again, the water is at 190 degrees Fahrenheit, and its inside diameter is 0.25. And the heat transfer, uh, I should say the heat transfer coefficient is 2275 BTUs per hour, foot squared, degrees Fahrenheit, like this. And then for the steel, its diameter, we determined, again, the outside of the steel, that's D2, that's 0.3125. This thermal conductivity of steel pipe is 50. Like this. And of course, for the thermal conductivity, uh, feet is not squared. Then finally, the insulation has a thermal conductivity of 0.013, and its diameter was 520833. And finally, for the soil, for soil Z, and I'll show you in a little bit why we're calling it Z, because we're going to use a table. Z was 4 feet. It was 4 feet below the surface. And finally, then over here, and then its uh, thermal conduct thermal conductivity was 0.012 BTU per hour foot degree Fahrenheit, like this. Next, we're going to look at the resistances. And let's think a minute what we have. We've got this pipe, and there's going to be like convection between the water, which is at 190 degrees. And again, this is going to be convection. So remember, convection is 1 over H times A. And then we're going to have conduction through the steel. But again, because that's a radial surface, remember the equation we use for that is log, and let me write this down. So the next one here is going to be log D2 over D1 divided by 2 pi KL. So again, this over here is between the water and the pipe. This is going to be through the steel pipe. Then we're going to have heat transfer through the insulation. That's going to be between D2 and D3. That's also going to be log D3, D2, 2 pi L. And then finally, there's going to be heat transfer, once it gets through the insulation, heat transfer up through the soil. And that's just going to be our standard um, uh, heat transfer, but we're going to be using the shape factor. So that's going to end up being 1 over K S, where S is the shape factor. And then finally, at the top of the soil, we're at 20 degrees Fahrenheit, like this. The situation we have. So now we're going to look at each of these individual resistances. So let's go right over here to this convection one, and let me call that R1. Let me call it convection, and that's going to be one. Now, one thing I just realized, we're probably going to need to calculate the length of the pipe. Remember, the pipe length was 3 miles. We want to convert that to feet, since everything else has been converted to feet. So length of the pipe is going to be three miles, which uh, if we multiply that by 5,280 feet per mile, that's going to give us 15,840 feet. So now let's calculate the first one, the convection, called R1 convection. That's going to be 1 over HA. And again, we know what H is. That was our 2275 BTUs per hour, feet squared, degrees Fahrenheit. Now we want the area. And again, that's going to be like the circumferential area times the length. And of course, the circumference is simply going to be pi d, and that diameter is 0.25 times the length. Like this. And then through the steel, so we're going to have heat transfer, or we're going to have a resistance through the steel. I'll call that 1 to 2, since that's going to be the heat transfer that goes from diameter 1 through diameter 2. And again, that's up here, log of D2 over D1 divided by 2 pi K L. And we said that D2 was 3125 and D1 was 0.25. Then 2 pi, and the thermal conductivity was 50. And then the length was our 15,840. So notice these first two resistances. So for this one, I got this, and when I put this in my calculator, 4.48 times 10 to the minus 8. So you can see these first two resistance are much, because the convection heat transfer, the resistance is going to be pretty low. And because steel is a good conductor of heat, its resistance is going to be pretty low. Now, the next one, the insulation, should be high. And that's going to be between diameter 2 and 3. So I'll just call it 2, 3. And diameter 3 was 520833 feet. Probably don't need all those digits. And D2 was 3125 feet. And the insulation, uh, its thermal conductivity was 013 BTU per hour with F. And the length was 15,840 feet like this. And then for the insulation, we get a resistance 3.95 times 10 to the minus fourth. So that's quite a bit more resistance. Again, these two tend to be very small because we have a very long length. Now for the soil, we're going to use to calculate this by using the shape factor. Now for the shape factor, we're going to have to use the back of the book. Now in my book, this is table 11.1, and we have a situation like this. We have a pipe buried underground. We have like a temperature up here, pipe buried like this. Now there's several equations here. If Z is the same as the diameter, then we use this first equation. But now if Z is larger than the diameter, then we use this equation or this equation. Now, uh, because now in our case, the Z is 4 feet, but our diameter is only 0.20. Well, actually, the outside diameter is 0.52033. So in our case, we can use this one. Now, if the Z is much, much bigger than the diameter, then you can use this equation. But the safest thing to do again, if Z is greater than D, is to use this equation here. This one is sort of more of an approximation, but you'll never go wrong if you use this one right here. And in our case, the two will probably give us very similar results, but I'm going to use this one just to be safe. So again, in my book, this was table 11-1 with Z greater than D. And again, in my book, I'll write this down, 2 pi L divided by the log of 2Z divided by D plus square root of 2Z D squared minus 1, like this. And so let's go ahead and put in all of our values. And I'm going to put this up here, 2 pi. Remember our length. Our length was 15,840. Then log. Once again, remember Z is the distance below the surface. In other words, the distance to the surface of the soil to the center of the pipe. Again, we said that that was 4 feet. And D is going to be the outside diameter of everything on the pipe. That's going to be the all the way out to the outer part of the insulation. That's going to be 520833. And then we're going to really have the same quantity inside here. And the feet are going to cancel, so I'm just going to write this is 2 times 4. And this whole thing is squared here. Minus 1 and the square root of that, then we want the log of that whole quantity. So when you put that into your calculator, you get something like this. 29,068.3 feet. And so now we want to find the resistance of the soil. And let me do it this way. So the soil is going to be, again, the equation we had up a minute ago was 1 over Ks. And the resistance of the soil, or the thermal conductivity, was 0.12 BTU per hour feet F like this. And this is 29. 29,068.3 feet like this. And we get something like this. So now let's add up the total resistance. So R total. And I'm just going to simply add up all the numbers that we've found so far. And they all have the same units, so I'm not going to put the units down. Going out these all up, we get 6.817 times 10 to the fourth hour Fahrenheit BTUs. So then finally, what we want to do is put this all into our heat equation. Again, we're going to have Q is equal to delta T divided by the total resistance. And our delta T, let's see what we had. Our water temperature was 190. And our surface temperature was 20 degrees Fahrenheit. And our total resistance was 6.817 times 10 to the minus fourth hour F BTUs like this. And that's our answer. 249,377 BTUs per hour is the heat transfer.